Hey everyone, and welcome back for another deep dive. Today, we're going to be looking at
Wonderful matrices.
wonderful matrices.
That's right.
And I know that sounds kind of like a
Sci-fi movie.
cheesy sci-fi movie
Yeah,
title,
yeah.
but it's actually a pretty groundbreaking new approach to designing the architecture of foundation models.
Right.
And remember, those are those AI workhorses behind so many things we use every day,
Absolutely.
from search engines to chatbots.
Every day.
And the source material for this dive is a research paper by Jingzhe Shi and Bingheng Wu.
Great paper.
And we're here to break it down for you.
Yeah.
It's
What's really fascinating here is that this research isn't about
creating something new,
creating a whole new model from scratch.
right?
It's really focusing on cleverly combining two existing approaches to foundation models,
Okay.
sequence transformation and state transformation.
Right. So it's like taking the best parts of two different tools and just kind of like merging them into one super tool. But before we get into how they do that,
Yeah.
can you help us understand these two approaches a little bit better? What exactly are sequence and state transformation?
Sure. So imagine you're reading a sentence.
All right.
Sequence transformation focuses on understanding the order of words.
Okay.
So how the words are arranged to convey meaning.
Mm.
That's what models like transformers excel at.
Okay.
They're great at processing information sequentially,
Mhm.
but they can become less efficient when dealing with very long sequences.
Okay.
Think of it like trying to remember a really long list of items in order.
Yeah.
The longer the list gets, the harder it gets.
Right. Okay. So that's sequence transformation.
Right.
What about state transformation?
State transformation is more about understanding the meaning behind the words, the overall message, or the context. Models like gated multi-layer perceptrons are better at this.
Okay.
They're great at capturing the essence of information, but they can be computationally expensive.
Okay. So I see the challenge.
Yeah.
One approach is good with order.
Right.
The other one's good with meaning.
Exactly.
But neither is perfect on its own.
Yeah,
And that's where wonderful matrices steps in.
that's exactly right.
Okay.
Wonderful Matrices attempts to solve this problem by combining both approaches,
Okay.
leveraging the strengths of sequence transformation and state transformation while minimizing their weaknesses.
Uh-huh.
It's all about finding that balance that leads to both greater efficiency and effectiveness in foundation models.
That's a really elegant solution.
It is.
So how do they actually pull this off? What's the secret sauce of wonderful matrices?
So the key lies in three innovations that the researchers introduce in their paper.
Okay.
And they call these innovations rotary position embedding,
Okay.
dynamic mask attention, and cross-domain mixture of experts.
Wow, those sound
Intense.
intense. Can we break those down one by one?
Sure.
Okay, let's start with rotary position embedding.
Okay.
What is it and why is it so important?
So rotary position embedding is a clever way to encode positional information into the model,
Yeah.
allowing it to track the order of information
Okay.
even while processing the meaning.
Okay.
This is essential for combining sequence and state transformation effectively.
Gotcha.
Think of it like adding timestamps to each word in a sentence.
Okay.
The model can understand both the word's meaning and its position in the sentence, which helps it make sense of the overall context.
So it's giving the model a sense of chronology, even when it's focused on understanding the bigger picture.
Exactly.
Okay, and what makes this technique so special?
So one of the key advantages of rotary position embedding is that it allows for something called linear fast inference.
Okay.
This means the model can process information much more efficiently, which translates to faster responses and better performance.
Okay.
It's like giving the model a shortcut so it can jump ahead in the process without sacrificing accuracy.
That's impressive.
Yeah.
So it's not just about combining these two approaches, but also making the whole system more efficient.
Exactly.
Okay, we've got rotary position embedding down.
Right.
What about dynamic mask attention? That sounds pretty intriguing too.
Dynamic mask attention allows the model to selectively filter information.
Okay.
Think about it like reading a long article. You might skim certain parts while focusing intently on others.
Right.
This technique enables the model to do the same, focusing on the most relevant information while filtering out the noise. This helps the model process information faster and more efficiently.
That's really clever.
It is.
It's like the model is learning to prioritize, just like we do when we're trying to understand something complex.
Absolutely.
So it can zero in on the most critical parts of the information.
Exactly.
Okay, what's the third innovation?
The third innovation is called cross-domain mixture of experts.
Okay.
And this technique addresses the challenge of optimizing the use of the model's parameters. So large AI models have a lot of parameters, but not all of them are equally important for every task.
Right. I could see how that would be a problem.
Yes.
It's like having a giant toolbox where you only need a few specific tools for a particular job.
Exactly.
Yeah.
Cross-domain mixture of experts allows the model to use its parameters more efficiently,
Okay.
reducing redundancy and making the model faster and less computationally expensive.
Okay.
It's like organizing that toolbox
Yeah.
so that the model can easily access the right tools for each task.
Okay, so we've got these three innovations: rotary position embedding for efficient processing,
Yes.
dynamic mask attention for selective filtering, and cross-domain mixture of experts for parameter optimization.
Right.
And all of this comes together in a specific model architecture they call CHEAMS.
You got it. That's where things get even more interesting.
Perfect. Let's dive into the details of CHEAMS and see how all these pieces fit together.
Sounds good. So let's explore the architecture of CHEAMS. It's like a well-organized factory with different stations working together to produce a final product.
I'm ready for the factory tour. Where do we start?
Okay, so the journey begins with word embeddings, which is like the receiving dock of the factory.
Okay.
This is where words from our human language are transformed into numerical representations that the AI can understand.
So it's like translating English into a language that the AI speaks.
Precisely. Each word is converted into a unique vector,
Okay.
or a list of numbers that captures its meaning.
Gotcha.
After the words are converted, they move on to the next station, which is called RMS norm.
RMS norm. Okay, does that stand for something?
It stands for root mean square normalization.
Okay.
And it's a crucial step for ensuring stability during the model's training.
Okay.
You see, when training a large AI model, the numbers can sometimes become very large or very small, which can cause problems for the learning process.
So it's like making sure the machines in the factory are running smoothly and not going haywire.
Exactly. RMS norm keeps the numbers within a manageable range, making the learning process more efficient and preventing errors. From there, the information travels along pathways called residual connections.
Residual connections. What's so special about those?
Think of them as express lanes within the factory. They allow information to bypass certain stations, preventing information loss and keeping the signal strong. In deep neural networks, information can sometimes get lost or diluted as it travels through multiple layers.
Right, so it's like making sure the materials don't get lost or damaged as they move through the factory.
You got it. Residual connections provide shortcuts so that the information can reach its destination without losing its integrity.
Gotcha.
And then, of course, we have the rotary position embedding, or ROPE, which we talked about earlier. Remember, that's the mechanism that gives the model a sense of order, like timestamps on each piece of information.
Right. That's like adding a tracking number to each item in the factory, so we know where it is and where it needs to go.
Exactly.
Okay, so we've got the words converted.
Yes.
The numbers stabilized. The express lane set up. And the tracking system in place.
Okay.
What happens next?
Next, we encounter the core components of wonderful matrices. The algorithms responsible for combining sequence and state transformation. First up is SSD, which stands for state-space duality. It's a sophisticated algorithm designed to efficiently handle long sequences of information.
So SSD is the sequence transformation expert?
Exactly. It excels at understanding the order and arrangement of information.
Gotcha.
And then we have DMAT, or dynamic mask attention, which you might recall is responsible for selectively filtering information.
Right. It's like the quality control team in the factory making sure only the best and most relevant information makes it through. So DMAT handles the selective filtering aspect of sequence transformation.
Yes.
What about state transformation? Where does that fit in?
Excellent question. That's where our third innovation, CDMOE,
Oh?
or cross-domain mixture of experts, takes center stage. It's the specialist in understanding the meaning and context of information.
So it's like the team of experts who analyze the materials and determine their best use.
Precisely. CDMOE ensures that the model utilizes its parameters efficiently. like a team of expert craftsmen who know exactly which tools to use for each task.
I'm starting to see how all these pieces work together, but it sounds like a lot is happening within this model.
It is. And remember, all of these modules,
Okay.
SSD, DMAT, and CDMOE, are carefully stacked and connected
Okay.
with RMS norm and residual connections strategically placed throughout the architecture.
Right.
It's a highly sophisticated and efficient system.
So it's like a perfectly choreographed dance of algorithms, each playing its part to create a harmonious outcome. But what happens after all this processing? Does the model just spit out the answer?
Not quite. Remember those word embeddings we started with?
Yes.
We need to translate the AI's output back into human-readable language.
So it's like sending the finished product back to the shipping department to be packaged and delivered.
Exactly.
Yeah.
And that's where the LM head, or language model head, comes in.
Okay.
It's responsible for converting the AI's numerical representations back into words we can understand.
Okay, so I've got the receiving dock, the stabilizing station, the express lanes, the tracking system, the sequence and state transformation experts, the quality control team, and finally the shipping department.
Right.
It's quite a complex production line.
It is, and it's this intricate interplay between all these components that makes Teams such a powerful and efficient model.
So this entire process from receiving the raw input to delivering the final output is what Teams does.
Yes.
And it's all guided by the wonderful Matrices architecture.
Right.
It's amazing how much is happening behind the scenes.
Yeah, it is. And the really exciting part is seeing how well this model performs in practice.
Right. We've talked a lot about the theory behind wonderful matrices and how Teams is designed.
Yeah.
But how does it actually perform? Does it live up to the hype?
That's what we'll explore in the final part of our deep dive.
Okay.
We'll take a look at the results of the researchers' experiments
Okay.
and see how Teams stacks up against other state-of-the-art models.
Okay, so time for the moment of truth.
Right.
We've learned how wonderful matrices works and how Teams brings it all together, but did it actually deliver?
Right.
What were the results of the researchers' experiments?
Well, the researchers were very thorough in their evaluation of Teams, testing its performance on a range of tasks and comparing it to other leading models like Llama 3, Mamba 2, and Jamba.
Okay, so they really put Teams through its paces.
They did.
What were they looking for in these experiments?
So they focused on two key areas, efficiency and effectiveness. So for efficiency, they measured how fast Teams could process information, both during training and during actual use. Think of it like evaluating both its learning speed and its performance speed.
Right, speed is essential, especially when we're talking about these large, complex AI models.
Absolutely.
But speed isn't everything.
Right.
What about effectiveness? How do they measure that?
To assess effectiveness, they used a series of standardized benchmark tests designed to evaluate the performance of language models. These tests cover a wide range of tasks, from understanding and responding to questions to summarizing lengthy texts and even generating different creative text formats.
So it's like giving Teams a comprehensive exam to see how well it understands and generates language.
Exactly.
And how did it score?
Teams performed exceptionally well, consistently outperforming the other models on most metrics.
Wow.
Especially as the models were scaled up to billions of parameters. This suggests that wonderful matrices is not only efficient, but also highly effective, especially when dealing with larger, more complex models.
That's impressive. So the combination of the hybrid architecture and the three innovations, rotary position embedding, dynamic mask attention, and cross-domain mixture of experts really paid off.
They did.
Does this mean the wonderful matrices is like the ultimate solution for building better AI?
While it's a significant step forward, remember that AI research is a continuous journey.
Right.
There's always room for improvement and further innovation.
That's a good point. Even with these breakthroughs, there's still so much more to explore.
Absolutely.
So what's next for wonderful matrices? What are some of the potential future directions for this research?
Well, the researchers highlighted several promising avenues for future exploration.
Okay.
One area they mentioned is investigating the impact of attention scores on layer depth.
Okay.
Remember that potential redundancy they observed in the attention layer?
Yes, the idea that there might be even more efficient ways to design these models.
Exactly. Further research in this area could lead to even more streamlined and efficient architectures.
Okay.
Additionally, exploring how wonderful matrices can be applied to other domains beyond language processing is another exciting possibility.
That's fascinating. So wonderful matrices could potentially have a broader impact beyond just language models.
It could.
It's incredible to think about the possibilities.
It is.
So as we conclude this deep dive into wonderful matrices, what are some key takeaways for our listeners?
Well, this research demonstrates the power of combining existing techniques in innovative ways to achieve significant improvements in AI.
Yeah.
It highlights the importance of efficiency and effectiveness in model design
Right.
and offers a glimpse into the exciting future of foundation models.
You've given us a lot to think about.
Yeah.
Thank you for guiding us through this fascinating exploration of wonderful matrices.
It's been my pleasure.
It's inspiring to see how researchers are constantly pushing the boundaries of AI,
Absolutely.
leading to breakthroughs that can potentially transform our world as we continue to explore the vast landscape of artificial intelligence. Who knows what other groundbreaking discoveries await us? That's an exciting thought to leave our listeners with. Thank you for joining us on this deep dive into wonderful matrices, and we encourage you to continue exploring this fascinating topic on your own. Until next time.
Stay curious.